Hello and welcome back. Today we are going to be looking at Idris, which is an interesting functional programming language, and we are joined by Zoe,
Hello.
who you can see here. And so tell us a bit about yourself and Idris and what we're going to be doing today.
So I've been programming in Idris for about 3 years now, and over that time I've started hacking on the compiler. But Idris itself, that's a dependently typed functional language. We'll get to what that means over the course of the stream. But it's a very similar language to Haskell, only the types can get a lot more complicated. And that also means you can have a lot more type safety than just regular Haskell.
Sounds good. Well, I'm a fan of Rust, so I'm a fan of type and memory safety stuff, so that sounds very exciting.
Yeah.
Okay, so let's have a look. We've got Idris all set up and installed. But before I forget, also in the description we've got a link to Zoe's channel where we've got a talk so far about something to do with the Idris compiler, I think, and probably more stuff coming out in the future. And I might make some videos explaining how to install it. It's fairly straightforward, but just need to wait for things to compile a bit. But it's all set up here, and we've got a brief. We've got a hello world, and you can see there is our wonderful result down there. So, do you think should we explain how it works?
Yes. So, similar to Haskell, every Idris function starts with the type declaration, this bit here. You've got the name of the function, and this colon means that the main function has the type IO, and then this symbol here. So IO just means that the main function interacts with the real world, in this case printing to the console, and this symbol is called the unit type, and it just similar to Rust, it doesn't convey any data or anything.
Right.
The second line is the actual definition of the main function, and this calls the putstrln function, which prints a string to the console followed by a new line, and it just prints this string.
Okay, that sounds fairly straightforward. And one thing, well, I suppose is different from some languages, well, a lot of languages like Rust, but is more common in the functional world, is that you use equals to assign to the function, and we don't use any brackets for function invocation. Is that correct?
Yeah, that's right.
Cool. So what are we gonna? What's the next step then? Oh, and sorry, just to stay down here, and then to execute it, we compile it with Idris 2, and then we do exec main, and that runs it.
Yeah. So I was thinking to start, we could learn about data types, and in particular an important data type called nat, which is short for natural number. So I'm going to get you to define it with some hopefully helpful hints along the way. So how would you define a natural number?
Well, I would say sort of strictly that it's an integer greater than 1, but I always think of a natural number as a sort of a number of things that you could have, a number that you can count to.
Yes, so in computer science, or at least functional languages, we always include 0
Right.
and
Okay.
positive numbers. Positive integers, I mean.
Yeah.
If you wanted to try and write that as a data type in Idris, can you think of how you do that?
Well, the main thing that I assume that you'd rely on is that if you start with 0 and then you add 1, then you can get all of the natural numbers.
Yes.
So would it be based on
exactly. That? Yeah. Do you know the syntax for data types?
No, I do not.
Okay, so let's open up a Rust file, and you can do it there to begin with, and then I'll translate into Idris for you.
Okay.
Just so you get the idea.
Right. So. Oh, you're way ahead of me. Okay. So, but in terms of, so would it be something like this, and then it would hold another natural number, wouldn't it? So it would be. Wouldn't you actually do? You could either have 0 or something else. Like that?
Yes, that's correct. Spot on. So
it can either be 0 or it can be that with 1 more than something else.
Yeah, exactly. One more we usually call suc, short for successor, or just S.
Mm-hmm.
So if we go back to hello-world.idra, this is what it looks like in Idris.
Right.
One sec. Because NAT is already defined in Prelude, you've got to hide it so you can define our own. So.
And the pipe there is meaning or a, but I'm assuming.
It does mean or, yes. So this means a NAT can either be 0 or the successor of another natural number.
Right, okay. Do you need to define what the successor is, or is that enough?
This is where you're defining what the successor is. It's
right, I see.
The constructor.
Right. Okay, oh cool.
So
and that's why you can pattern match on S with a natural number. S and then something else.
Yes. You'll get this, I imagine you'll get this quite quickly. So if you define, this is just a shorthand for defining multiple functions or global variables at once.
Right.
I'm
assuming those are the same. I'm assuming this is the same thing.
They all have the same. Yeah.
Right.
So then 0 is going to be something. This one's quite an easy one.
Yeah. So that would just be Z.
Yeah.
And then could we define 1 as being this S0?
Yeah.
And then the same thing with 4 would be SSS1.
Yeah. That's spot on. A useful thing to do with natural numbers is to add them.
Mm-hmm.
So do you want to have a go at writing this function?
So if we're going to have, if we do x, y, what we want, no, because we need to decide which one we're going down. So if I do s like this, then I'm going to return plus x and then s, y, and then if we have plus z, y, then that's equal to y.
Yes, that's a slightly unusual definition. Usually we have the s here.
Oh, I see. Right.
But they are equivalent.
Okay.
But I will go with this definition because that means the later functions can be easier.
Right. Okay.
And
I guess that does actually makes more sense.
yeah. And another one. So the reason why we have this S here rather than for the Y is that often you might know that, well, when you're proving something about a natural number, you might know, for example, that some natural number x is S of Y. And then that means if you have plus x z, this will reduce automatically to S of plus yz. And then we know, then we have a constructor at the start of this reduced expression, which is very useful. If you defined it the way you did initially, get this, and this would reduce instead to plus y s of z. And now we have a function here, and it's often harder to prove things about functions than it is about constructors.
Right, I see.
So that's the reasoning for having this s in this place.
Okay.
Just a bit more practice before we move on. Define an equals function.
So what I was also, is there, because in the way that I think about it, this is sort of the base case. Do you normally put that first or second, or at the beginning or the end of?
People usually put their clauses in the same order as the data type declaration. So in this case, you would have said first.
Right.
The clause order can sometimes matter because
because I'm assuming if multiple clauses match, it goes by the first one.
Yes. But here, Z mutually exclusive, so it doesn't matter.
Right.
True and false have a capital.
Okay.
Yeah.
So then, if we take equals x, we want sx and sy. Then we do equals xy.
Yeah. If you have a look at the error message.
Equals is not covering missing cases. Oh. Right, and then we want equals z equals false. And then do we need to do both of them like that?
Yes, you do need to do both of them.
Okay.
So if you move this final clause after here, can you spot any way you can make this a bit shorter? So what I mean is,
so because we know that both of them aren't 0, so how does that help us?
Here we know the left one. Well, we know that they're not both 0, and we know that they're not both S, which means one of them has to be S, one of them has to be Z.
I see. So
you don't care which way round it is.
Can we do that?
Yeah.
Right, I see. Oh, that makes sense. Because if they're both 0 or they're both non-zero, then we would already have hit a case. So by the time we've got to this line, we know at least one of them has to be 0, and it doesn't matter which, because we know that means
exactly. Yeah.
Oh, cool.
Okay, you seem to have mastered natural numbers. So now let's move on to vectors. In Idris, a vect is a linked list that has a specific length.
Right. As opposed to a vector in something like Rust or C++, which is more like an array and has...
Yeah.
and has contiguous memory. Okay.
This is a more complicated data type because it has a natural number here.
Right.
This is similar to Rust const generics. In that, rather than this could just be a. I'll start with list to show what I mean. A list is just a vec that doesn't have a specific length.
Yeah.
We might have an empty list.
Yeah.
And this is just a list of any type. And we could have this is an operator called cons, which is just 2 colons, and it has the head of the list, the tail of the list, and that makes another list.
Right.
There we go.
So are these operators on the type empty and cons?
These are constructors.
Oh, I see.
So
Okay.
in Rust syntax, this would be an list T is either empty or cons T list T.
Right. Okay. So that's
And now if we
that's just like when we did the natural one with the pipe, except now it uses where, and then I'm assuming that's true. You can just split it up over multiple lines.
you can split this up over multiple lines, but this is called GADT syntax, generalized algebraic data types. It's a
Right.
scary name, but you don't really need to care what it means.
Okay.
Each line is a different data type.
Right. I see.
So you have different constructors. You have the constructors on the left, followed by a colon, followed by the type of the constructor.
Okay.
And this will be more important for vectors. We could define lists using this sort of syntax, but when we use for vectors, we have to be a bit more careful. So I'll let you try and write this.
The vector. The vector
yeah.
definition. Okay.
Yeah.
So we'd have empty again for this, but then would that be would you do 0? Would you do something like that?
Yep. I'll comment this out because you can't have two things with the same name.
Oh,
the same
right.
namespace.
Okay.
Because we've defined that ourselves, we can't use that.
Oh,
actual numbers. We have to use Z.
Right.
Yeah.
Okay. And then we have cons.
Yeah.
So that is going to take A and vect so it takes something of any type and a vector of that type, and then it produces a vector of that type with one more, so with its length being the successor of the original vector.
Yeah, exactly.
Okay.
So now let's write a list of them. If we have a vect of, I'll do 4 instead. So if you have a vect of 4 natural numbers, So the reason I've put main here, that's the name of the module. If you don't give it a specific name, it's just called main.
Right.
But we need to put main here because otherwise for will be treated as a local variable rather than referring to the global variable we defined earlier.
Right, I see.
So if you want to just pick for that and write them in a vector.
So would then I just say, so would that be with square brackets?
We haven't called this nil, so you can't use square brackets.
Right.
This empty constructor.
So
But
what I'd want would be, so I'd have empty, and then let's say 4, and then like that.
almost. So you can't just put the equals here. You need to write it as an actual
Oh, okay.
clause. I made that mistake once in the Idris compiler in a PR I made, and I didn't spot it until a few weeks later. Fortunately, it didn't seem to break anything.
Oh, is this
You might
because
as
is this because we've have our own implementation of NAT?
Yeah. We might as well try and fix it. So if you look at the error, it says can't find an implementation for num nat. Num is an interface, which is like a Rust trait.
Yeah.
If you go into the terminal in the in Idris 2 and then do :doc num with a capital N. You can see there's a few types. Plus, which we've already defined. Times, we haven't defined that yet. We can just leave that as a whole for now.
Right.
And the important one, from integer. So from integer is used to convert a literal number into a nat.
Right.
So to write an implementation, if we go back up to a bit after plus, you write the interface followed by the type you're implementing it for, followed by where, and then you have to define all of the functions. So that's x plus y, x times y, and from integer.
So further x plus y, could we just use the plus function that we previously defined?
Yeah.
So I could do plus x y.
Yeah.
And then from integer, could we do the same thing? Is there a successor for integer? Could we?
No, integer is a built-in type. It's compiler magic, really. You have multiple. You can compare it to another integer. You can add, you can subtract, and anything like that.
Right.
So
would we do a similar thing, but just so could we say that something like from integer 0, and then have like a another thing, then we return that, and then does that make us?
So you mean sort of pattern match on this integer x here, yeah?
So if we had so if I do
you can write it here if you would like.
But wouldn't I need 2 arguments?
Why would you need 2?
To hold the Because the way I was thinking of it, if I just call it from int, I need to. That means I just that you could. So this would be. That if you had 0 and then if you had from int I n that equals from int I minus 1. Will I need to put those in parentheses?
Yeah.
And then the successor to n.
That works.
And then
you can also. So what you could also do is, yeah, I'll let you write that first, and then I'll show you how I'd write it.
Okay.
So how I would write it is. From integer of 0 is 0. From integer of the integer 0 is the natural number 0.
Right, and then from integer I is the successor to from integer of I minus 1.
Yeah.
Right, yeah, that's a lot simpler.
Yeah, so this dollar operator, it doesn't really do anything. It's still the successor constructor applied to this bit. It just means you can have fewer brackets.
Right, okay.
And if there's something Idris and Haskell programmers like, is having fewer brackets. Yeah.
It's sort of the irony, because whether this gets compiled, it gets compiled to scheme, and then it has all of the brackets. So.
Yeah.
Yeah. Okay. Right. Let me. Okay, so and now that has solved this error here.
Yeah, it has.
Excellent.
What did I have next? Okay, so appending two vectors. I'll let you write the type for this as well.
Okay. So this is going to take vect if we have n a Is that right?
Yeah, that's right.
Okay.
So do you want to use like interactive editing to write this one? That might be a good demonstration.
So let me scroll down a bit so I can. So so we'd probably want this one, wouldn't we?
I can't see your pop-ups, and I can't see the screen.
Can you see?
Okay, that's written the entire thing.
That's
useful. I did mean doing like one step at a time, but
okay.
It just is really impressive sometimes.
Right. Okay. So the base case is if we're taking things out of the first vector and putting them into the second vector, then our base case would be that there's nothing in the first vector, in which case it would be, how did we define vector? Oh, it's right here. If it's empty, then y, then we just return y.
Yep.
And then if we have then we'd want to do append with x's and then x, then cons y, like that.
Okay, I'll just do some. Hang on. Right. This isn't right, but it'd be interesting to see what it does. So give me 1 sec. I'm going to do some type magic to make it work.
Right.
Oh yeah, that won't work. Okay, I'll get rid of our definition of nat just for a sec,
Okay.
so I can. And is that no? Oh, I forgot to do that. Okay, there we go. Is this going to work?
Everything seems to be commented out for me now. Ah, now it's back.
Okay. Okay, so now if you go to the terminal with Idris is.
Yeah. Here we are.
And then do :R to reload it. Yeah. So now if you try appending 2 vectors, and make sure the left one has at least 2 different elements.
Could I do it like this?
If we rename empty to nil.
Ah, right.
Okay. And then if you reload again.
Ah, right, let me just... Right, so it hasn't maintained the order.
No, it hasn't. So where should this x go in the final vector?
We want that one to go at the front.
Yeah, so when I go to this, we want the x first, followed by...
Oh, I see. Right. And then here we'd have append if I can figure out how to type x's y like that.
Yeah, exactly.
And then we get what we want. Right, okay.
Yeah. Okay, so I was thinking next we could move on to a slightly more interesting example of dependent types.
Okay, sounds good.
So we can get rid of all of this for now. I'll just comment it out if I can type. So let's define a sort of syntax, well, a sort of toy language and a well-typed interpreter. So well-typed means that it's all type safe and you don't you can't you don't have to worry about something being the wrong type.
Right.
So this data type is an expression, and the type of the expression is going to be the first argument of the constructor.
Okay. Right, I see.
So we might want a constant integer. So this just takes an integer and it wraps it into an expression that returns the type of integer.
Right, I see. Okay, that makes sense.
We might also want to add things. So this takes the left argument, the right argument, and it returns another expression.
Right.
What do you think left and right are going to be?
Iants. So they're both. They're just going to be expressions, aren't they?
Yep. But what sort of expression? If you just put, let's just try putting expression here. It doesn't like it. Because on its own, expert isn't a type, it's a bunch of types.
Right.
And
So
you need to specify what type of expression it is.
Would it have to be iant?
So iant is a constructor, not a type.
I see. Oh, so then expr int?
Yeah.
Right, okay. So, like this.
Yeah. So what this is saying is the add constructor, it takes an expression that returns an int, and another expression that returns an int, and it isn't, and itself is an expression that returns an int.
Right, okay.
Make sense?
Mm-hmm.
And now we can add an interpreter for it, which takes an expression which returns A, and it just evaluates it into that A.
Right. That makes sense. So then if we have could we have e int n returns n? Oh, wait. I need equals. Would you need brackets for that?
Yep.
Okay. And then that has, I'm not sure how you do this one.
So first of all, how many arguments should add have?
2.
Yeah. We can call them x and y, for example.
Like that. But each of those are going to be, would we need to do that?
No, you need recursion here, because it won't necessarily be an int, or an int.
Oh right, that could be add as well.
That could be add as well, yeah.
So what we want to do is we want to do inter x then plus inter y, like that.
Yeah. That's right.
Right, and then that will recursively call the so then we could have any number of adds.
You could, yeah. And let's make it a bit more interesting and add some other types to our language. We can have less than for comparison. So what's the type of e less than going to be?
That's going to be expression that returns an int, expression that returns an int boolean.
Will it just be a boolean?
Oh no, it would have. Oh, well, if it's less than, then yeah.
Specifically, it'll be an expression that returns a boolean.
Oh,
not
right,
just a
okay.
boolean.
Sorry, yeah, that makes sense.
Yeah.
So it would
So
be.
do you want to write that? Yeah.
Right, because it would still need to be evaluated.
You're too rusty. You keep writing. Yeah.
Yeah, primitive types always are now lowercase in my head.
No, in Idris, that all types are uppercase.
So we'd have x, y, and then it would be oh, right. Right. But then could we just do that?
Yeah.
Okay.
Okay, now for a slightly, well, a more interesting expression, if statements. What was this going to be?
So we'd want but could we have a generic type here like this?
Yeah, you could. You'll need another
But it can be an
expression.
Right. So, but can you? Because could you do something like this? As in,
So
it can return an expression, or would that have to be another? Or I suppose you could define another variant of expression. That.
no, so in functional languages, you always have if expressions, not if statements. Which means they always have to return a value.
Right.
That means you need an expression when it's true. You also need an expression when it's false, and then you
Right.
need it to return an expression.
Right. Okay. My point was just that you could have. I'm assuming you could implement some kind of unit type in this interpreter. But.
You could. If you wanted, we could change this a bit, and instead of having this, we could make it return a maybe A.
Right.
Maybe is an optional type. So if this is true, then we return this. Otherwise, we don't return
nothing.
anything. Yeah.
Right. Well, let's stick with the one that. Let's stick with that one.
Yeah.
So, okay. So here we want if. So we have. So the first thing we'd want to do is oh right, yeah, it does that for me. So we'd want to get that boolean, and then how would we actually do that? How do you do if statements inside Idris?
If something, then what happens when it's true?
Yeah.
Else, what happens when it's false?
Right, I see. So we do if this, then. Oh, sorry. Then we'd want into x, else into y.
Yeah, that's right.
Okay.
This is a very simple language, but I think getting more complicated, it gets complicated fast.
Right.
Are there any other things you want to learn about Idris?
I'm not sure. This seems like a pretty interesting place to start. And it's interesting how quickly you can get something like this working. So
Yeah.
could we actually write a sort of a simple math program? I guess you'd basically be writing at the. This basically is interpreting AST, isn't effectively?
Yeah. So we could write an example. that returns a integer. And let's say we write if 7 is less than 4, then 8 plus 2 else 6.
Okay.
So if you try and write that in this language.
Right. So the first thing that we'd want is to do the E that, I'm assuming. So then, oh yeah. So then that predicate would be that's going to be less than. So if this is going to be 7, this is going to be 4. Then here.
So if you save it now, then we can just deal with this bit here.
Oh, right. I'd need to do.
Not exactly. Expression is a type constructor rather than a regular constructor.
Yeah.
Yeah.
Okay. And then here we'd want E add, and then we're adding int 8, int 2, and then this is just going to be int 6.
Yeah, so I will I'll add some indentation and stuff to make it a bit easier to read.
Okay.
For everyone. So yes, if 7 is less than 4, then we add 8 and 2. Otherwise, we just return 6.
Yeah.
Perfect. So I was thinking we could also do some theorem proving in Idris.
Okay.
So Idris as a dependently typed language allows you to prove facts about your program.
Mm-hmm.
So one thing we can prove
and
is...
also, I don't have very much experience with it, but these things like less than add, these seem like functions. So this is sort of... I guess, I mean, it is a functional. So this sort of is... And it kind of looks like Lisp, not that I've done very much, but
it looks like Lisp because you have lots of brackets.
I guess so.
And
but
also because they're all regular prefix functions. They could just as well be infix operators,
right.
And then it would look a bit different to Lisp.
But it does seem... No, I just think that's pretty neat. And then... And then if you wanted to make a full interpreter, you'd probably want to write something that parsed whatever you wanted your code to look like into some structure like this.
Yeah, so you'd need both a parser and you'd probably want to parse it into an untyped language first.
Right.
And then have a type checker which will convert it into a typed variant.
Right,
this.
I see.
Yeah.
Sorry, yeah, on the theorem proof.
Yeah. Theorem proving. So the first one we want is, so we know anything plus 0 is equal to just n.
Yeah.
The thing itself. If we want to prove this in Idris, we might write like plus 0 right neutral. This is what it's called in base. neutral just refers to it doesn't do anything.
Right,
It's
okay.
like the identity function, basically. So if you have some natural number n, then n plus 0 is just equal to n.
Yeah.
I'll write this one first so you can have a look. So if we're adding 0 to anything, then so now we have this. These names of holes are just keyboard smashes, really. They don't have much meaning.
Okay.
So if you hover over right hand side, this hole here, you'll see it has the type 0 equals 0.
Yeah.
And there's a special way of proving this called REFL, which stands for reflexive. And because 0 obviously equals 0 and they are exactly the same thing, you can just have REFL.
Right, I see.
So now if you hover over REFL, you'll see the type is x equals x.
Right.
Which says that, well, that's quite self-explanatory.
Yes.
The more interesting case is the S case. So now we hover over it, we get S of plus k0 equals S of k.
Yes.
How are you? What are you thinking about?
Oh, I see. So that's right. So that's basically saying you're going sort of one level down, and you're saying that if we have k is the predecessor to whatever number we have now, if you add 0 to that, you still get the same thing, and then that's going to go all the way down until you hit 0.
Yeah, exactly.
Which you can use the reflexive thing to say, well, 0 is equal to 0. And so,
yeah. So we might first think, just call plus 0 right neutral with k. This doesn't have quite the right type. Because if you hover over it, it's k plus 0 equals k, but what we want is S of k plus 0 is S of k.
Right, so do we need to wrap that in S?
Yes, but you can't just call S on it. Because this is an equality type rather than a natural. So we use the cong function, which is short for congruent. And the type of cong, if I can spell and type, if you have some function f, which is the type a to b, then, and we know that hang on, we have x and y are both of type a, and there's a function f which has type a to b.
Yeah.
In other words, it converts x or y into another thing. We know that if x and y are the same, then f of x is the same as f of y.
Right.
This is a property special to functional, purely functional languages. And this basically, it states that if you call f with a value and you call it with another, and you call it the same value, you always get the same thing out.
Yeah. But that's only true if f is a pure function.
Yes, but all functions in Idris are pure.
Yeah.
Even the main function is kind of, in a way, pure.
Because it returns what IO needs to be done and then something else does it.
Yes, exactly. The only really impure function is one called unsafe perform IO.
Right.
And you should only use that if you know what you're doing. Yeah.
Okay.
So this is your first theorem that you've proved.
It's very exciting. I've always wanted to prove that if you add 0 to the number, it's the same number.
It's a good test that your definition of plus is correct, though.
I suppose so, yeah. If that's not true, you've really messed something up.
Yeah, yeah. that's all I'd really prepared.
Okay, that's fine.
We could wrap up now.
Yeah, definitely. So I think that was very interesting. Might do some other things if there's other topics you think would be interesting to go over, and just in general, either in Idris or in something else. It would be interesting to look at making an interpreter or a simple compiler, sort of building on what we did today. So maybe we can discuss that. But I hope that was interesting, and I hope to see you again. So thanks for watching, and bye.
Yes, bye.